mass M2, or how you tune the K2, how you tune the C2, so that to satisfy the performance required by yourself, by the designer. All right. Now this is something that I will show you the demo, a little demo here. But anyway, this is from Mathematicas. Let me just show you the little demo here. All right. And we'll see how it works. Okay. If you look carefully here, see you can, if you look at this, let it run. And the long one, that's a spring without TMD. The upper one, the upper one is the same system but with the TMD. Now, when you change the K2 over K1, we'll show you this, how it works. For example, if I change my K1, K2 over K1 and run it, it doesn't move. I don't know why it doesn't move. It's not moving anymore. This is from Mathematica program. Reset. Okay. All right. Now it moves. Now you can see the differences. All right. Every time you change, if you change this to be larger and larger, and then we call reset, then you can see that the motion will be a little bit different. So how we tune this? What is where this, in what positions the K2 divided by K1 will be best for the performance? Or what is the best ratio, M2 over M1, giving you the best performance? Another one is, what is the C2 divided by K1 that will give you the best performance? This is all kind of questions. So in this class, we'll learn how to tune it. So like 101, they tune it this way too. Of course, it's not the way I tune it, just try and error. I move up this and move there and see what's going on there. It's not like that. They do have some analytical way to do the optimum, we call optimum design. All right. And this is just to give you some of the example. Later on, I have some other demo to show you what we can do about it. This way. All right. Now there's another pendulum motions. This chapter I just try to tell you some of basic motion and how can we write a differential equation for very basic motions, the pendulum motion. We know this is much easier. There's nothing easier than this. All right. I don't know why this is jumping to there. It doesn't matter. Now, this is the equation of motion to describe this pendulum motions. M d squared theta divided by d to dt squared. The theta is this angle. That's from x to L. That's the angle. This is the theta. All right. And then plus mg. M is the mass. G is gravity. The sine theta divided by L equal to 0. That's the without external force except the gravity force. Then this is the equation of motions. We know. I think you all know this equation of motion now. What is the differences between this one and this one? Tell me. Right? This is say again. This one. Well, there's a big difference between this one and the spring. You know, the spring. If you look at the spring, is, do you remember that spring? Where is this guy? The spring is m x double dot plus kx equal to 0, right? For the spring, right? Now what is the difference between this one and what is the difference between these two?
It's not linear.
This is nonlinear, because this equation is nonlinear. If the sine theta is nonlinear. But for small theta, then for small theta, say sine theta is very small, then this becomes dt square d2 theta plus g over L theta equal to 0, right? This boy is not really friendly to me anyway. And so these two equations, basically they are the same in mathematical sense. So for small angle, the spring motion and pendulum motion are the same in terms of the ordinary differential equations. So when you learn this, now let us look at, there's something move there. Did you see that? I think, let me just do this guy here and see what's going on. All right, it's supposed to be like that. Let's see what's going on. Yeah, that's better. Okay. Now, this is the motions you're supposed to have. You have A is accelerations. The direction of the acceleration is changing all the time. They change the directions of A. And V is the velocities is also changing in the directions. Okay. Although equational motion of this and equational motion for the spring is not the same, but when you plot the motion, they look different because this is in terms of angle theta, and another one, the spring, is in terms of the linear displacement. One is angle, one is linear displacement. That's the differences. So when you solve these equations, then you plot it, you can see this is the motion you have. That, if you look carefully, that's a spring you got. All right. To this point, to this end, we learn how to model a spring, how to model a TMD, how to model a pendulum motions. And all of this involve ordinary differential equations. So we got to learn how to solve the ordinary differential equations. Now, in your undergraduate studies, most likely in sophomore or in junior, you have the class called engineering mathematics. And in there, it teach you how to solve the homogeneous equations. Now let us review. I think Dr. Huang already spoke a little bit about ordinary differential equations. Now this is the ordinary differential equation. It's very common, and then some students even know this during high school. But let me just refresh your memory about this. I need to refresh your memory so that you know that what I'm talking about. All right, I assume this is all the real constant matrices. I will focus on some explanations of the differential equation with the real system. All right. So this is the spring mass system, and assume we have that the m equal to 1. Let's see. All right, and assume m equal to 1, c equal to 3, k equal to 2, then this is the differential equation we got. So that's the spring mass system without any force applied to it. And how can we solve this? And this is, you can see that that's the spring and desk part here. And your homework, I also that the show you how you model a vehicle or a motorcycle when it ride on the wall. What kind of the equation of motion you have. Based on that, you can solve and what kind of vibration you're going to get. You solve it, you will see what happens. And that's the equation of motion for this system. All right, just for this simple system. Now,